Okay, so today we're continuing looking at the definite integral by understanding area under a curve. So some of this may be a little bit repetitive, but it's just slightly different than what we were going over before. So we know that using Riemann sums, okay, and taking the limit of R ram sum n, that it will equal the area under the curve for a non-negative function. And that it also, our area for a non-negative function could be represented by this integral. But now we have something new, okay, that if f of x is a non-negative function over a closed interval, like we had before, the integral of f of x with respect to x from a to b is also the total distance traveled, okay? Which would make sense because if you remember, we did use either a left Riemann sum or right Riemann sum in our table, and that was to get like the total distance, for example, of the bottle going upstream. So this is another way that you can do that, but this is only if you know the function. If you're given a table, then you are going to have to use an approximation method, like your left Riemann sum, like LRAM, right Riemann sum, like RM. If f of x is a negative function, then area is the negation of our integral, okay, f of x with respect to x from a to b. This is also the total distance traveled. So just kind of keep in mind what I said before about if your function is below the x-axis. So it kind of leads into, okay, so I know a little bit of this is repetitive, but I do want you to copy this down because you are going to be given problems about the distance traveled, and you have to use an integral to find that distance. All right, so we're up to here. If f of x is a function over a closed interval from a to b, and it looks something like this. Okay, let's say this is a, this is b. Then the integral of f of x with respect to x from a to b is the area above the x-axis minus the area below the x-axis. So obviously the way I drew this, let's make up some numbers so you can understand this concept, okay? So if this is an area of 10, and this is an area of 2, okay, then this integrands, hold on, this is f of x. Ta-da! Okay. Is going to be 10 minus 2. Okay, so you're getting 8 for its area. We call this the net change or displacement. So I want you to like underline it, make sure that you label that, because a lot of times you are asked about the displacement of a particle, body, object, or it may even use the words net change. I mean, it's the same thing. So it's not necessarily the two areas added together. That would be 12. It's they were subtracted. The only reason it was subtracted because one is positive and one is negative. Okay, net change or displacement, the answer can have a positive or negative sign. Keep the sign with that, okay? All right, so there's one other thing that I just want to go over, and that is our positive function. Okay, so we went over area under a curve here, and our negative function. Area under a curve here. And then let's say we have a function like I just went over. One piece is above the x-axis, one piece is below. So let's say we graph our function. This is horrible, but we bounce it to our x-axis. I did not draw this very well. Okay, I'm gonna try again. We bounce it to our x-axis, and let's say the area here is 7, and the area here is 7. So what happens is that we negate this part, okay? It's minus that part, and this remains positive. So the integral of this function, whatever this is, who knows the way I drew it, okay, when bounded to the x-axis, is 0, okay, from this value of a to b. If I change a over more, which is why I moved it in the first place to make it look symmetric, if this was smaller, then we'd have the situation like before. If this was smaller, then we'd have a negative answer. So it depends on what our graph looks like. So there's one more thing that I want to go over. The integral of a constant. If f of x is c, where c is constant on the integral from a to b, then the integral of f of x with respect to x from a to b is the integral of c with respect to x from a to b. And all we need to do with that is c times b minus a. Right? And there is a way to kind of prove this with limits. I may show this on the board in class. But I'm going to get to our example using this situation. So a train moves along the track at a steady 75 miles per hour from 7 a.m. to 9 a.m. Okay, so what does that mean? Graphically, okay, we're looking from 7 to 9. I'll put a break there. And it's steady at 75 miles per hour. So this is your velocity in miles per hour. Okay, time is in hours because I'm using 7 and 9. So express the total distance traveled as an integral. So we went over how the total distance is the integral from a to b of a function with respect to the variable of our function. So let's take a look. Our function looks like this. It's steady from 7 to 9. So our lower limit is 7. Our upper limit of integration is 9. Since our function is our constant 75 miles per hour, it's in respect to time, I'm going to write dt. That's why I said of whatever variable our function is of. And even though it's a constant, take a look at what variable you have down here. Okay, so this is our expression. You have to know how to set up integral expressions. And if you look now to evaluate it, we do just need the area under the curve, and it is a rectangle. So with a rectangle, okay, you have base times height. And we can see the base is 2 and the height is 75. So our answer for total distance is 150 miles. Remember, we're talking about distance. Okay, so it's got to be the miles and the miles per hour. Okay, so this ties into what we were doing in our last lesson. We can see a shape there we can use. So go ahead and use that. So good luck.